Hello friends, in the last video we had discussed what is thermal noise. Thermal noise is one of the types of internal noise. It is due to the resistances. It could be the resistance in a resistor, resistance in a semiconductor, it could be resistance in a resonant circuit and so on. Now we move on to the next type of internal noise, that is short noise. Short noise is basically seen in DC, that is direct current crossing a potential barrier. It means that it is a random fluctuation that takes place in any direct current crossing a potential barrier. The holes and electrons do not cross the barrier simultaneously. That is a random movement of the holes and electrons. Therefore, short noise is seen in diodes, BJTs, due to the bias current crossing. Short noise normally occurs when there is a potential barrier. PN junction diode is an example that has a potential barrier of 0.7 volts. When the electrons and the holes cross the barrier, short noise is produced. Therefore, we see short noise in a diode, a transistor, vacuum tube, and so on. A junction diode will typically have two components of noise. One, that is thermal noise due to the resistance, and the other is short noise. If the active device provides amplification, like a BJT, the noise also gets amplified along with the signal. On the other hand, a resistor normally does not produce short noise since there is no potential barrier built within a resistor. Short noise, like thermal noise, is frequency independent. It is small compared to the DC value. It is not observed during measurement of DC, but significantly it is observed in amplifier circuits. Short noise can be measured in the form of mean square short noise current and is given by IN square is equal to 2IDC QE PN ampere square, where IDC is the direct current in amperes, QE is magnitude of electron charge, that is 1.6 into 10 raised to minus 19 coulombs, and PN is the equivalent noise bandwidth, which is measured in hertz. This is a small example to show you how to calculate short noise. Calculate short noise component of current present on a direct current of 1 milliampere flowing across a semiconductor junction, given that effective noise bandwidth is 1 megahertz. My dear friends, please keep in mind the units that have been given to you. Over here it has been given that the DC current is 1 milliamperes and the effective noise bandwidth is 1 megahertz. It is expected for you to know the electron charge. So IN square is equal to 2 into 10 raised to minus 3 into 1.6 into 10 raised to minus 19 coulombs into 10 raised to minus 6 hertz, which comes out to be as 18 nanoamperes. The next type of internal noise is partition noise. As the name suggests, this noise occurs usually where the current divides. We know that there is a random fluctuation in the division. The number of electrons and holes which cross or divide at a junction are random, and therefore partition noise occurs wherever current has to divide between two or more electrodes. This results from random fluctuations in the division. Therefore, diode is less noisier than the resistor. The input stage of microwave circuit is a diode circuit. Therefore, it is less noisier. Gallium arsenide FET draws zero gate current, and hence it is used for low noise microwave amplification. The spectrum of partition noise is flat. Next type of internal noise is flicker noise or low frequency noise or pink noise. Flicker noise is due to impurities in the material, which in turn cause charge carrier fluctuations. Active devices, integrated circuits, diodes, transistors all exhibit a low frequency noise since we have intentionally put impurities in the material. This is a frequency dependent noise. Till now, the types of noise that we saw were all frequency independent. That means the amount of noise that was being produced was the same for all the frequencies. But flicker noise or low frequency noise is a frequency dependent noise, and therefore it is also called as the pink noise since it is unequal distribution of noise. The relationship is 1 over frequency. That means flicker noise is equal to 1 by f. The mean square value is found to be proportional to be as 1 by f bracket raised to n, where f is the frequency and n is equal to 1. The next type of internal noise is burst noise or popcorn noise. This is another type of low frequency noise. It is observed in bipolar transistors. In this case, the noise appears as a series of bursts at 2 or more levels, like noisy pulses. In audio system, this noise is more evident in the form of popping sounds. Source of this noise is related to the presence of heavy metal ion contamination. Gold dope devices shows a very high level of burst noise. The last type of internal noise is avalanche noise. As you all are aware of avalanche effect. What is avalanche effect? It is whenever a diode is reverse biased, the reverse bias characteristic of a diode is such that there is a region where the reverse current increases rapidly with slight increase in the magnitude of reverse bias voltage. This is the region which is called as the avalanche region. Holes and electrons in diode's depletion region gain sufficient energy from the reverse bias field, and this results in collision. Collisions always occur at random, thus giving rise to large noise spikes in avalanche current. For example, in Zener diodes, we have seen that Zener diodes are usually used as voltage reference sources, but the avalanche noise creates a problem. The spectral density of this noise is also flat. That's all for now. Thank you. More videos to come to your way. Thank you.